Let's begin. The next topic is an orphan topic. I sometimes put it with curve fitting, but it's not curve fitting, it's more related to data analysis. But then you could argue that interpolation is also kind of data analysis, but it's not. But we don't have much about data analysis. Regression is like data analysis, but it's not 100% data analysis without statistics, which we will see in the spring. So this next topic is an orphan topic. One of my TAs in the past used to call it part of numerical calculus, the numerical calculus section, but it's just one topic or 1.5 topics, as you will see. So let's get started on that. It's called numerical integration. I do not have a movie or anything about that. I used to have like a funny poem about it, but it was so lame that I decided not to do it anymore. I don't know if it's in one of the recordings a long time ago, but I hope nobody finds that. Okay. So we're done with curve fitting. What was that? Oh, interesting, interesting ringtone. Okay, so we're done with the second unit. We started with errors, kind of intro to numerical methods. That's not even a unit. We did solving linear equations, solving algebraic equations, sorry, linear or nonlinear. And then we did curve fitting. We understand now why solving linear and nonlinear equations was the first thing, because everywhere we went, there was a linear system or a nonlinear system we needed to solve. Before we embark on the last unit, which is solving differential equations, so solving algebraic equations, solving differential equations, I would have loved to do them back to back, but I can't because many of you are just taking differential equations. So I want to give you a chance to get some mileage with the math department so that I appear, it's easier when I'm teaching it, like, oh yeah, now it makes sense, because it'll be the second time you see it, so strategic decision. But also I need numerical maturity, if you want. More training with Python, more getting to know each other and talking, and setting the stage for differential equations. Really, it's a question of not whether you're able to comprehend it, but how well you'll be able to comprehend. So that's why I leave it to the end, and we squeeze in the curve fitting in the middle. Now, this topic is an orphan topic. It's related to data analysis of discrete data. Call it numerical integration. And we start with this plot, looking at the metric tons of CO2 emissions per capita worldwide. So per person worldwide, how many tons of CO2 were committed per year, per capita. Okay, starting from 1960 all the way to, I think this stops here at 2016. I think I might have newer data later in the text in Canvas, but it looks like this. And the question is, how, if you're given this data, think of it as having a table. Let's say you have a table, 1960, you got 3.15, 1961, 1963, and so on. You have a table, year and metric tons of CO2. How would you calculate the total CO2 emissions for all of those years? Give me some ideas.
Well, you can find like the area.
The area?
You can find the area under the curve, but then
Okay.
some of your data points.
Okay, so let's build on that. Area under the curve, that's correct, because you're kind of adding up all of those. So what is the curve?
Like the model is it? Or
Like, okay, area under the curve, but what is the curve? Right, so how do I calculate that area under the curve? You're thinking of an integral,
yeah.
correct? Because it's numerical integration. But also like, okay, the integral of what?
Well, this one we don't really.
I have discrete data.
If we have discrete data, so could we regression model and then take the integral under that?
Sure. Okay. We're pretty darn hard to do a regression model on this though, right? Because the data is quite variable. Maybe you can split it into sections. One section, like first part, do linear, but it's not going to be exactly spot on. Okay. What else?
Maybe you take like previous ones, so you turn it into squares, and sort of like a very, very large amount of it.
A very large what?
Amount of like rectangles, and then take the area of the.
Okay, so rectangles between what and what?
So maybe like a few points, and then rectangles.
Okay, so essentially you're saying you're gonna, between each pair of points or every 3 points, you're gonna draw either a straight line, okay, or just to draw a horizontal line, build rectangles under all of those and just add them up, right? Do you think just summing up the y values would work too? Yeah, you just need to account for the area, right? Because you need to have the unit distance also on the x-axis. So if this were not a unit here, if the distances were different, you'd get in trouble with that. So you'd have to account for that. Okay, what else? Those are good ideas, and they are correct ideas. Okay. What else? Yeah, that's about it, really. Okay. So we are going to build on the idea that your colleague said, the Riemann sum idea. And although the regression is interesting because it does give you a model, we can do a much more accurate calculation, okay, by looking discretely at the data itself. And starting by the idea that I could just sum up the y values together and add them together to compute that area under the curve, like these little rectangles. Okay, so that's what we're going to build on. At the end of this chapter, I hope that you'll be able to define what quadrature and numerical integration means. Hopefully, with all these quizzes, you're going to come out like dictionaries, coming out from this course. Calculate the area under an analytical function using what we call the Newton-Cotes formulas. Calculate the area under a discrete set of data points using Newton-Cotes formulas. So numerical integration would also apply, and our purpose is to also apply it on functions where you cannot find the integrand by hand. There are complicated functions, e to the minus x squared and stuff. You can't do it by hand. You have to numerically solve it. There's no analytical answer for some integrals. So you have to numerically evaluate those integrals. Okay? So we will learn about that, doing it discretely and for analytical functions. Use the left point, right point, midpoint, trapezoidal, Simpson's 1/3 and 3/8 rules to calculate the integral of a function. So we're going to learn a lot of techniques to compute the integral under a curve. Okay, starting with an analytical curve. Now those apply to all of those apply to an analytical function, but not all of them, as we will learn later, apply to discrete data. Some of them require the data to be equally spaced. Some of them do not apply at all. Some of them are incredibly complicated to apply. We will learn that the trapezoidal rule is one of the best ones to use on discrete data. And then I'll show you some error estimates in just one slide. Error bounds for midpoint, trapezoidal, and Simpson's rules. Essentially like the maximum error you would commit. Okay. Our problem here will start by posing the question, if I'm given a continuous function, I'm giving the analytical formula, this curve looks like this red curve over here, and you're asked to find, so you're given the function, f of x, and you're asked to calculate the integral over some region going from a to b, whether you know how to integrate this by hand, or most importantly, not. What do you do? How do you compute that? That's a pretty useful thing to know, right? Okay, so we'll start with the only thing we'll learn this year is our Newton-Cotes integration formulas, and they're pretty easy given that you know how to do interpolation. The Newton-Cotes integration approach essentially approximates the function f of x as a polynomial and then integrates the polynomial analytically, okay, to find the answer. That's all there is to it. Okay? So we're going to take the function f of x, approximate it as a polynomial. Could be a 0th order polynomial, 1st order, 2nd order. Just do an approximation and then integrate that by hand because we know how to integrate polynomials exactly. So you integrate that by hand so you can document all of those formulas and then find the answer. There's 3 steps. You choose the order of the polynomial. So this will determine the number of points needed to determine the coefficients of the polynomial. So think back about interpolation now. Let's say you have a curve and you're like, okay, this looks like a quadratic. So I need a 2nd order polynomial, therefore 3 coefficients. So I'm going to pick 3 points on that function to approximate my function as a parabola. You pick those 3 points, you approximate it with those 3 points, you do the analytical integration and you're done. Then choose the points where you want the polynomial to go through and find the coefficients, and then integrate the polynomial exactly on the interval in question. Okay, so we will start with, so keep that in mind. This kind of, you might be saying now, this is a terrible idea. Like you have a highly variable function, like a sinusoidal function, and you approximate it with a straight line. Yep, that's what we're going to do. Okay, but then there's a trick that we will make it very, very accurate. Okay. We will start with the simplest approximation, and that we call the left, right, and midpoint rules. Okay? The simplest polynomial approximation is essentially a polynomial of order 0, and in other words, approximate the function as a constant. Okay? Just approximate the function as a constant. So f of x is approximately equal to c. And then you say, okay, I'm going to approximate f of x by s integral c dx. That's going to be b minus a times that constant. Okay? Now, how do you choose that constant? Okay, there's a few ways. The first and simplest way is to choose the constant to be the value of the function at the left interval. So in other words, we're approximating that entire red curve over AB as simply f of a. So you get this rectangle, and therefore the area under the approximated function is b minus a times f of a. Okay? This is called the left point rule. Why? Because we chose the left point to approximate the function as a constant. Okay? What other choice can we do? What other point can we pick? The right point? Yep. Okay, so we can do the right point. That's correct. We can choose the right point, f of b, on the right, to approximate the entire function. And see how I draw that line? Because I'm saying that entire change in the function in the right, I don't care about it. It's all going to be equal to f of b over that interval. Right? So that's why I draw that horizontal line, because I'm approximating the entire function as a constant over that interval. Then this is called the right point rule. And then the integral is approximated as b minus a, which is this width over here, times the height, which is f of b. Okay. There's another way. There's actually an infinite number of ways. Could you choose any point in between a and b? Absolutely. You choose any point between a and b. Now, in the absence, because all of these points are equally valid, information theory, that's kind of probability stuff, tells you the best one to choose is going to be the midpoint. And in fact, that gives you the better accuracy. And if you choose the point in the middle, so this point in the middle at a plus b over 2, and draw a line there to approximate the function, what it does, like in this case, it tends to balance the effects. So when we chose f of a, we underestimated that portion of the function. When we chose f of b, we overestimated this portion. The midpoint tends to balance that effect. Whatever you overestimate on the left side, you're going to underestimate on the right side, or vice versa. Okay? So that's called the midpoint rule. And again, in that case, the area is going to be b minus a times the height, which is f of a plus b over 2. Okay. Now, there's a little caveat here that will become a problem when we are dealing with discrete data. So here we're dealing with continuous functions that you can evaluate anywhere. So you have f of x. So you can evaluate f of a, f of b, f of a plus b over 2. You can evaluate it f of a plus b over 3. It doesn't matter. You can evaluate it anywhere you want because you know f of x. When you choose the midpoint, you need to be able to evaluate the function at that midpoint. This will not be the case with discrete data. We will worry about that once we get there. Okay. These are going to be our first 3 approximations for functions. Obviously, they're going to be horrible when we are taking very large intervals, but we're going to fix that in a minute. But first, I want to show you how horrible they are. And I want a tool to compare our answers to. And I'm not going to do analytical solutions, so I want a built-in tool in Python that can do numerical integration for continuous functions. And that built-in tool is Quad. It comes from SciPy. Okay, so write that down. That's going to be your go-to utility in Python to do numerical integration on continuous functions. It comes from the integrate subroutine in Python in SciPy. So from SciPy, you import integrate. And then you say integrate.quad. You give it the function name, and you give it the interval, a and b. Very simply. And inside it, it does some magic. It numerically computes the area under the curve between a and b. Okay? So we are going to hold that as our gold standard. So in whatever we're going to be doing next to compare our left point, midpoint, right point rules to integrate a function, we're going to compare our results and see how terrible they are and compare them to Quad. Okay? So here's a summary of what we've got. And like I said, when the interval is so big, I mean, these are going to be horrible approximations, right? I'm taking a sine function or function that varies exponentially, right, and then has some wiggles in it. Obviously, these are going to be bad approximations, but that's okay because we're going to fix that in a minute. All right. So our first activity is going to be to create 3 Python routines that implement the left point, right point, and midpoint formulas. Those routines should include the function. So I'm going to create a routine called my left point rule, and I'm going to apply it to an arbitrary function, okay? Not specifically for sine or cosine. So we're going to define the function separately in its own routine, and we're going to pass it to the integration subroutine. We're going to do one for left point, one for right point, one for midpoint. Also, the arguments need to have a and b on which the function needs to be integrated. Okay. Now and then we're going to use those routines to compute the integral of 1 plus half sine squared 1.75 pi x, this integral between 0 and 1, and we will compare our results to SciPy's Quad routine. Okay. Now, if you go on Canvas, under the modules integration, there is a notebook with gaps in there for these activities, for the entire, all the activities for this lecture. Okay, so you can download that, and we will work with that. I'll move the slides here for a second. Okay, so window. Okay, let's see if I can find it. Integration. It's called Quadrature with Gaps. Okay, so if you download it and open it, you should see something like this. Oops. You should see something like this. We're going to do, this is going to be our first activity. I have a bunch of question marks here. So download this subroutine and this notebook, and we'll start working on it together. I'm going to make a copy of it with gaps and call it in class 2024, class fall 2024. Okay. All right. Do we have it? Download it, up and running? All right. Okay, so let's start. Let's import NumPy, etc., matplotlib, and this time you need to import integrate from SciPy. Okay, from SciPy, import integrate. because we want to compare our answers to the ones from SciPy. The first activity is to develop these 3 routines. Okay, so first I want to look at how this function looks like. Okay, I just kind of want to get an idea of how this function looks like. And I have a bunch of stuff here defined for you to plot it in a beautiful way and show the area under the curve. But the most important piece here that you should know is just a subroutine that I defined to evaluate my function. Because I want to plot it. I want to look at it. I want to see how it looks like. Okay, I want to understand it. Right? So when you execute this, it gives you an error. Because I didn't, what? Okay, oh, there you go. Okay, so this is my function. It looks like 2 mountains, right, and a couple of slopes here. And I'm highlighting the area between 0 and 1. I'm filling it with a gray color, okay? Just to kind of illustrate. You can do this with using fill in between. It's just a little trick, but you don't have to do that. So we need to compute the area under this curve. Okay? Now, you can tell immediately if I were to use the left point rule between 0 and 1. So the left point rule is going to evaluate just this integral, so it's going to miss these 2 guys here. The right point rule is going to go in the middle, which is kind of nice. It tends to balance things out. The midpoint rule is probably going to be worse because it's going to draw a point here in the middle, and it's going to evaluate the area under that. So my prediction here is that the right point rule is going to be the most accurate in terms of answer in this case. Okay? All right, so let's start by doing the left point rule. All right, I'll help you with the first one. So my condition was that the routine arguments need to include the function name and the interval over which we are evaluating. So it does include the f function and a and b. And so I need to return here b minus a times f of a. Agreed? So that's the left point rule. What's the right point rule? b minus a times, so if you look here, right point rule was b minus a times f of b times f of b. And finally, the midpoint rule was b minus a times the function evaluated at the midpoint, which is a plus b over 2. Okay? So now I define my computational routines. And now simply I can just call each one of those on my function, my f, between 0 and 1. Right? So if I do left rule on my function, and from 0 to 1, it's going to give me an answer of 1. Okay? Let's do right rule on my f from 0 to 1. It will give me 1.25. And midpoint rule for my function 0 to 1 is going to give me 1.07. Okay, now my prediction was that the right point rule is going to be the more accurate one. So let's compare. We're going to do quad, integrate.quad. That's going to be our high accuracy or gold standard. That's going to be our truth, the true answer, what we're going to treat as the true answer. So for quad, I need to give it the function name and a and b. That's it. So I'll pass my f and then 0 and 1. Okay, so it gave me an answer of 1.27. Okay? So as I expected, the right point rule was more accurate for this function. Why? Because it tended to balance whatever we overestimated and underestimated because of the oscillatory nature of the function. Yes?
Could we just like for a study where we're evaluating that, could we just take the average of all the values? That seems like extra.
No, there's a better way. Okay. There's a better way. Yep. There's a better way. Okay. Okay, so far, no mystery, terrible approximation. Okay, but we're going to take that and make it so much better now. Can we move on? All right. Let's go back. These are how my slides look like in real life. I have a lot of hidden slides here. Oh, that was the poem, I think. It's hidden somewhere, okay? And the TAs do not have access to those original slides, so they cannot show them to you. Okay. Let's continue now with making this a little bit better. Okay. So now you recognize that, okay, we can apply this over a big interval, but because I know the function f, I know how to evaluate it anywhere. How about we take that big interval and split it into smaller intervals and apply the left, right, or midpoint rule to any one of those smaller intervals? Do you think that's going to increase our accuracy? Yes, absolutely. Immediately is going to increase our accuracy. We have all of that information. We have the interval A and B, so we can split it into 100 intervals or 1,000 intervals. And then on each one of those subintervals, we have the local A and B for that given interval. We have the function. We can evaluate it at anywhere in that smaller interval. So we can apply the left, right, or midpoint rule on any one of those subintervals. That will immediately increase your accuracy exponentially. So to increase the accuracy, we can take that interval and subdivide it into smaller intervals. We're going to use linspace to do that. And then immediately we increase accuracy. This procedure of dividing the area under the curve into smaller areas is called quadrature. The word comes from quadrilateral elements, which was a technique used to split land in old days in agricultural land. What is the area of your land? What is the area of my land? And they would stand like this, and then they would start splitting it into small rectangles, quadrilateral elements, and compute the area of each one of those quadrilateral elements. So that procedure is called quadrature. So from here onwards, if we say quadrature or numerical integration, we're going to equate to mean the same thing. Okay? Numerical integration from here onwards equivalent to quadrature. Okay. This is also called a composite rule, taking the continuous function and splitting it into small areas, decomposing it into small rectangles, and applying that rule onto each one of those small rectangles and adding them all up together. That's called the composite rule as well. Okay? So this is going to be our plan. We're going to take the function. We're going to split it between A and B into subintervals. And then we're going to apply the left, mid, or right point rule onto any one of those subintervals. And that becomes very obvious because once you're at a subinterval, all you need is the left point, the right point. If you're doing the left point, you do f of the left point, f of the right point, or f of the midpoint. And then you have to add them all up together. Okay? So let's do that. We're going to create now a Python code that computes the integral of an analytical function with an arbitrary number of segments. So now we're going to pass the function a and b and also the number of segments that we're going to subdivide that interval to. How many segments do you need? Well, this is similar to Taylor series. How many terms do you need? Okay, how many terms do you need? We can compute a relative approximate error and say, okay, stop after we have accomplished that tolerance. Okay, we're not going to do that right now, but that's the procedure I would do in practice and say, okay, keep adding those, keep doing those segments until we reach a certain tolerance. Okay, so it's a little bit involved to program that because you need to try with 10 segments and then redo the integral with 15, redo it with 16, redo it with 17, so to find the exact number of segments. Okay. All right, so let's do this now in Python. And I already have some code for you here. Develop a Python code that computes the integral for an analytical function with an arbitrary number of points, interval n, all right? And do that for the left, right, and midpoint rules, okay? So now look at the code. It's become significantly more, not significantly more, but it's become more tedious because now I need to go ahead and take that full interval A to B. I need to find a way to split it into subintervals. Linspace is going to come to the rescue. And then I need to loop over those points, each one of those points or the segments if you want, and then apply the midpoint or the left point rule individually. So we'll do the first one, and then we'll let you do the others. Okay, so we will start by taking the left point rule. The first thing I want to do is do my linspace. And the question you need to ask is, how many segments do you want? So the function, the routine interface requires f, a, and b, and n is the number of segments, not the number of points. Each segment has 2 points, agreed? So each one of those segments has 2 points. So for n segments, I need n plus 1 points. Okay, if you decide that n means segment, and you say that in your function definition, n is the number of segments, then that tells you what needs to be here for linspace, because linspace works with points. So if n means segment, then in linspace I need n plus 1 points. Okay? Now, if you meant by n to be the number of points, then the segment is going to be n minus 1 segments, right? Okay. I like to use segment, so I'm going to create a linspace from A to B with n plus 1 points. Okay? Because n segments, that gives you n plus 1 points. Now, my result for the integration, I'm going to initialize it to 0, because I'm going to sum the integral here, if you don't see kind of what's going on under this. Let me perhaps move this a little bit up. So the plan is to go over each segment, evaluate the left point, midpoint, or right point rule, and then add it, keep it stored, and then go to this one and add it to this, add this to this, and so on. So I start with an initial value for my result, for my integral answer as 0. And now I'm going to loop over the segments. Okay? So how do we decide? I need a counter. So I have now n plus 1 points. So they're going from x1 to xn plus 1, or x0 to xn, because the indexing starts from 0. So I'm going to start with for a range going from 1 to n. Why? Because xi, actually I can start, I'm going to go from 0 to n, right? Because I'm going to start at x0, and then I'm going to do I plus 1. And then once I get to the end, the last entry here is going to be n minus 1. And so I plus 1 is going to be x at n, which is the indexing in the array for Python, right? Okay, so that works. Okay, so xi plus 1. Agreed? So I'm going to start I at 0. My first interval is going to be x0 and x1. Sorry, the indexing here is not consistent with Python indexing. With Python indexing, the first entry is going to be x0. The second one is going to be x1. Okay? So when I equal 0, this would be x0. This would be x1. When I equal 1, this would be x1. This would be x2, and so on. Now for the left point rule, so I am now living in segment I to I plus 1. My result is going to return simply on that interval b minus a times f of a. Okay, see how I defined a and b over here to just keep things looking the same as the formula. Okay, so that gives me my left rule. So let's go ahead and try it. I'm going to take it out of here so it doesn't crash. Make sure that everything is working. So I'm going to run it. I'm going to try now left rule, my f going from 0 to 1. Let's put 100 segments. Oh, look at that. It gave me 1.27. If you remember the answer from quadrature, it was 1.272, right? 1.273. So if I put 200 intervals, it's going to, look at that. It's starting to converge to the answer that quad was giving us. Okay, because we put more segments in. All right, now go ahead and do the right point rule and then the midpoint rule. Okay? You're just going to copy and paste from what I did here. Okay? But you have to make the correct adjustments. Okay? If you don't remember what the right point rule is or the midpoint rule is, you can Google it or find it here. Okay? So that's the right point rule and the midpoint rule. And this is the one we just did with the left rule. Everything is going to be the same except result. Once you code that up, go ahead and apply those composite rules on my function. Your fancier, got the Patagonia, got like cheap Costco stuff. It's like once you have kids, you just buy dad clothes from Walmart.
This is from grandma, so.
Okay. We're both matching. You in Patagonia too? Okay, so once you get that, done, go ahead and run it for the function we were just working with. Our answer is in the vicinity of 1.273. Let me know if you need help, any question, anything confusing. You got it? Yeah.
What line is it? 129.
Oh, you're still stuck at the left row?
Yeah, it's just giving me an error.
Okay, let's go to the code. You're going from xi. Let's see what the error is. Scroll down. Unsupported operand A. Yes. Okay, so it's in your math. No, scroll to the left rule. What equal b minus a times f of a. So your function, show me your function. My f, oh, it should be working my f, right?
Mm-hmm.
Yeah. Let me see, please.
Yeah, go for
If you
it.
don't mind. Oh, then space just goes from A to B, right?
I got
Yeah.
it.
Okay. So, Ooh, are you calling a float object?
I'm not sure. I just like did these.
Yeah, but what is the, where is the error coming from? Show me, scroll down. Yeah. So it's
Yeah,
coming,
it is from the result.
yeah, so my f, is it working? Yep, it should be okay. But a float object not callable, it means you're doing like a variable, like a floating variable, like b parentheses of a. So you're calling something on a float,
Okay.
and that's coming from
There. Result.
b minus a times f of b. And when you apply the right rule, b minus
Should I
a.
restart the kernel? Could it be that?
I don't know. Try restarting it, but I don't see anything. Oh, result plus equal.
Oh.
Yeah. Okay. You have a question? Okay. Let's do it. So with the right rule, yeah, we're gonna go length space. Again, segments are n, so points n plus 1 points, a to b, n plus 1. And then the range, we're going to start from 0 to n, xi plus 1. So that's our interval. And then result for the right rule is going to be b minus a times f of b. Okay, and then here, same thing here. Length space a to b, n plus 1 points, and segments. Range going from 0 to n. So we start at x0, go all the way to n minus 1, but we need I plus 1, so n minus 1 is going to be n, which is the last entry in the array. And then finally, for the midpoint rule, is b minus a times f of a plus b over 2, right? Okay, so now we can call the left rule right rule and midpoint rule, they're all giving us consistent results, highly accurate. With the more segments you add, obviously you're going to get more accuracy. You're going to hit a point where you're no longer improving. The way to fix that is to do a relative approximate error, but that means you need to kind of keep adding segments over and over again to try to estimate that error, or use some other error bound. So we're not going to do that here, but just to give you an idea of how this composite rule works. So obviously when I started explaining we're going to approximate a function with a constant, we're still doing that, except we're approximating it on a small interval. And it kind of makes sense. On a very small interval, the function, it's not changing that much. If it's exponential in nature and changing very, very, very fast, you need more intervals over there. Okay? You might have functions where the change, actually that's a great homework problem. You have a lot of change in a very small region, and then it slowly changes in the rest of the region. So what you could do, you could put more intervals in the fast changing region and less intervals in the slowly changing region. Okay? We can do that as well. All right. 3:10. Looks like we're not going to finish this today, but that's okay. Okay. Good. Yeah, I got the code. Okay. So this is for continuous functions. That's good. But that's not our only curse. Dealing with continuous functions, we need to work with discrete data. Okay, so given discrete data, the intervals are already defined for you, correct? They might be equal size or not equal, but they're already defined for you. Okay, let's see if the left point rule applies. The left point rule applies readily because on interval 1, you have the left data point determined for you already from the data, so you can use that to approximate the change, the supposed change in the function that's invisible to you because you don't have the analytical formula for these data. You just have discrete data points, but you can use the left point to approximate it over that interval. Same thing over here on any interval, you have the left point. So you're going to sometimes undershoot, sometimes overshoot, but you can readily apply it to discrete data. Just use the point to the left. What do you think about the right point rule? Do you have the right point for a given interval? Yes. Okay, so the right point rule also applies readily. Okay? Now, what about the midpoint rule? Does it apply to discrete data and under what conditions? Remember, with discrete data, you don't have the value between 2 points. So what do you do?
Would you use like 3 points? So just get the point.
Okay, so you skip every other point. So you take 3 points, right? So let's say for these guys, instead of going x1 to x2, you go x1 to x3 and use this one as the midpoint. Okay, would that work all the time? What if the data is not equally spaced?
It would be pretty inconsistent, inaccurate.
Yeah, it wouldn't be the midpoint rule anymore. Sometimes it would be the 1/3 rule or the 1/5, I don't know, right? So it wouldn't be called the midpoint rule. So that's the problem with the midpoint rule on discrete data, is that if the data is equally spaced, you would have to skip every other point and take that midpoint as your function value to evaluate the integral and sum them up, which could be a nightmare from a coding perspective. It's not a nightmare. I mean, you could do it with slicing, but it still takes some effort to do that. For unequally spaced data, it doesn't apply. It doesn't work for unequally spaced data. Is there another option we could do? So I've heard people in the past say, how about we interpolate? Okay, so we can take these 2 points and we make an interpolation, like a straight line interpolation between the 2 data points and find the value at the midpoint. You could do that, but that's not creating new information for you, okay? That's not creating any additional knowledge in the system because you're bounded by the interpolation. So you could do that as well, do a straight line interpolation. But there's a better formula for that, which called the trapezoidal rule. Okay, we will learn that in a minute. Okay. So yeah, this is what you would need to do for the midpoint rule, like we discussed. But for unequally spaced data, you can't do the midpoint rule unless you do an interpolation. Now, we learned quad as a Python tool for continuous functions. For discrete data, the Python equivalent that we will use is called trapz. It's like a trap, but it stands for trapezoidal rule. It is one of the most accurate and simplest numerical integration approximations for discrete data that you could use. Okay? So we will use trapz. It comes from NumPy. It's funny, SciPy gives you quad, NumPy gives you trapz. SciPy is more working with analytical solutions, analytical functions, continuous stuff. NumPy is more working with discrete stuff. So in np.trapz, you're given y data and x data. You give it in that form, the y data and the first argument, x data second, and it does numerical integration for you. And the data does not need to be equally spaced or anything. And we will learn that in a minute. Okay? So now we are going to try to do the left point. So from what we know so far, only the left point and the right point rules are immediately applicable to discrete data without doing any funny business or like skipping points. You just take discrete data, take the left point for each interval, and move on with life. Okay, so we are going to go ahead and test this idea out on the CO2 data discretely, and we're going to compare it with trapz. So what we will do, we will take x, y data for metric tons of CO2. So we'll have this data in Canvas in a second, I'll tell you. And using the left and right point rule, we'll develop a Python code that does numerical integration for discrete data. So we did it for a continuous function. Now we're going to do it for discrete data. There's two different approaches. Apply it to calculate the world emissions of CO2 per capita, and we're going to compare our results to what we're going to call the gold standard in Python is going to be numpy.trapz, the trapezoidal rule. Okay? You will need to download the CO2 world emissions.txt from the Canvas integration module. Okay? So go on Canvas, and there should be a CO2. There should be a CO2. Second here. There should be a CO2 integration module. Download the CO2 world emissions.txt file and put it right next to your Jupyter notebook. Okay, so we can just load it up. We've never loaded a text file yet in Python. That's okay. This will be the first time to load it up. I'll show you how very simply. We will do more of that in statistics. We'll be dealing with more data in there. But just to show you what this file looks like, if I go, it's just a simple x and y data. So on the x values is the year 1960, and on the second column it contains the metric tons of CO2. Now, because this data is only numeric, there's no text in it or headers, etc., we can just load it up in NumPy because it's just numbers. Okay? So the way you do this is say data equal numpy.load txt and just give it the name. So it's already there in that notebook with gaps. You just need to download this file, put it next to it. And then you can extract the xi and yi data using slicing, because this data contains a two-dimensional array. So it has two columns. This will give us the first column, and this will give us the second column. Okay, so everything in the first column and everything in the second column. And if we plot this, you get exactly that plot that you obtained. And you can also print out the data to see that I'm not lying. So print data, and you see this data over here, which is exactly the same as the data that's here. Okay? So we just load it up in NumPy. Okay? Okay, did I undo? Okay, so it looks like we need to looks like I deleted some cells as well. Did I delete something? Activity 3. Okay, yep. So edit, also undo. Okay, there's no more undos. Okay. So I have two routines here for the left point rule and the right point rule for discrete data. And in this case, I know we're out of time. We just finished this. If you're okay, a few more minutes, please, and I'll let you go. So in this case, we're dealing with discrete data. So the arguments, the function arguments are going, I'm going to assume they're going to be arrays, xi and yi. So I'm just going to call it xi and yi to stress the idea that this is an array. And the result is the answer of the integration is going to be initialized to 0. And I need the number of points in the data. And that's going to be the length of either one of those arrays, xi or yi. Agreed? Okay, now I'm going to loop over the data points. Okay, so we're going to start from n for I in range 0 to n minus 1. Okay, because we have n data points. Right? Now the array goes from x0 to xn minus 1. The range is going to go to n minus 2, but I'm going to have an I plus 1 here. So the n minus 2 plus 1 is going to get me to n minus 1, which will be exactly what we want. So A is simply xi at I, and B is xi at I plus 1. Now, f of A, I don't have f of A as a function evaluation. It's simply from the y data. So that's why I call it fa is simply yi at I. So that's the left point. Okay, it returns result. Now the same thing is going to apply here. So xi, yi, same thing, n length xi, and going 0 to n minus 1. Okay, A is going to be xi, B is going to be xi plus 1. Now fb is going to be the point to the right in the y data. So it will be yi at I plus 1. Okay? Make sense? All right. So now we can apply the left point rule, the left rule 2 on my xi, yi data for CO2. It gives me 232 metric tons for 1960 to 2016. And the right rule 2 gives me 233. So they're pretty close to each other. If we want the gold standard, we do numpy.trapz and say xi, yi, and what? No, yi, xi. My bad. So trapezoidal rule takes them in the opposite direction, y and then x. Okay. So trapz gives me 232.8. So it's kind of somewhere between those two. Trapezoidal rule is more accurate than either one of those. We will learn it on Tuesday. Okay? Thank you. Godspeed. Have a good weekend. Bye-bye.